All right, so what is the derivative of a function? All right, the definition is that the derivative of a function f of x is another function, which we're going to call f prime. So this little symbol here, this little like apostrophe after the f is, we say that f prime of x. That is another function that outputs the slope of the line tangent to the graph of f of x at the input x value. So the derivative of a function f of x is a new function based on that original function that deals with the slope of its tangent lines. And that's what it outputs. So the way we'll define that mathematically is we'll write f prime of x equals, and then we'll do a limit as delta x approaches 0 of the difference quotient, f of x plus delta x minus f of x all over delta x. So that exact thing defines the derivative of a function. So that exact limit, which is why we've been practicing doing limits like this back in chapter 2. It's because they're very important. So the process of like finding the derivative of a function, that process is referred to as differentiation. So we're going to spend a lot of chapter 3 learning about differentiation and different strategies for differentiating, which is different strategies for finding the derivatives of functions. And in general, finding like instantaneous rates of change for one variable with respect to another when they are somehow dependent on each other. Now, before we dive into all that, we need to establish some notation, because notation is very important in mathematics. It's what we use to communicate ideas, and there is unfortunately not one single system of notation that we use. Instead, we have several different forms of notation, all of which have their qualities and perhaps detriments. So there's good and bad things about all these different forms of notation, and so we'll use all of them in different situations. So first of all, let's look at some different notation for the derivative. The notations are due to different mathematicians. So I have 3 names of mathematicians here. I have Newton, Leibniz, and Euler. Newton is Isaac Newton of gravity fame, that the very same. Isaac Newton and Gottfried Leibniz who was German. Newton was English and Leibniz was German. They were 2 mathematicians who were both studying the tangent problem and the area problem, problems that had been around since the Greeks. And these problems had been eluding people for generations. And Newton and Leibniz both around the same time developed like the first ideas of calculus that were able to like succinctly and definitively answer and solve the like tangent problem and the area problem. So there was sort of a debate about who invented calculus, who did it first, and we've sort of historians have kind of settled on the conclusion that they basically did it independently of one another at about the same time. So they both get credit, but they came up with different notations. So the notation which is derived from Newton's work is this f prime notation. So this would be the notation for meaning the derivative of function f. We also sometimes use y prime. Since f of x and y are often interchangeable with one another, y prime is another notation for that. Later we'll be using, for higher derivatives, we'll be using like double primes. Later you'll see like f prime prime, which is the derivative of the derivative, and y double prime like this. So there are some examples of types of Newton notation. Leibniz used a different notation. You remember that I'll just write it in the top corner here, we were dealing with this like delta y over delta x, right? So Leibniz came up with this notation, which is dy over dx. And this means the derivative of y with respect to x. Another way you can write that is like d over dx f of x. That's if you wanted to write it as in terms of the function f. So that notation, the dy and the dx, mean they're called differentials, and we're going to talk more about what they mean later on. But for right now, you can think of it like a delta y over delta x kind of situation, except the dy and the dx are these infinitesimally small changes in x and y related to each other by the function. We will later talk about what dy and dx mean independent of each other, but for now I think the best way to think about it is dy over dx, this entire notation, means the derivative of y with respect to x. So don't really think about that as a fraction right now. And the d and the y are not multiplied together. That's not what's going on here. It's more like delta y, where it's like one thing, and delta x is like one variable. So right now, think of this as a chunk, as one big piece of notation that just means the derivative. Later, we're going to be getting to derivatives of derivatives, rate of change in the rate of change. And yes, it goes on as many times as you want. And that notation looks like this. And I can explain later why it is that the squares are in the exact places where they are. That's d squared y over dx squared. So I'll explain later why it is exactly like that. But so that's our Leibniz notation. And then there's Euler. Euler is a mathematician who came along later and did a bunch of things. And Euler is like one of the most prolific mathematicians of all time, rivaled perhaps only by Erdős. Sorry. But Euler was a pretty big deal, and Euler did a ton of work in developing calculus further and sort of improving on what Newton and Leibniz did. And he has this notation where he just said, well, if we want to do the derivative of something, let's just use a big capital D to mean derivative. And if it's with respect to x, we'll put a little subscript x, like that. And then put that in front of your f, and that means the derivative of f with respect to x. And then you can do it of x, or you can do dxy, like that. So it's capital D with a little subscript x, and that means derivative with respect to x. You'll notice me saying with respect to x a lot, because it turns out that you can calculate the rate of change in one variable with respect to other variables. So like, say for example, your velocity depends on time, but maybe also depends on your position. Then you can take a rate of change in velocity with respect to time, but also rate of change in velocity with respect to position. That's not a great example because that's not too realistic. A more realistic example might be like the temperature of air in a room, right? And that might be different depending on what point in the room you are, like how close you are to the vents or the heater or whatever. But it also is dependent on time, because maybe over the course of the day it gets warmer and then colder again, right? So like you can have a function which depends on more than one variable, and then you can talk about the rate of change in that function with respect to each of the variables, and that, like, it's different depending on which variable you're considering the rate of change with respect to. So the benefit of Leibniz and Euler notation is that they both have built into the notation, they say what variable they are differentiating with respect to, which is, for us, for now, it's going to be x almost all of the time. We're not going to get to the multiple variable stuff until like 2 semesters from now when you do Calc 3. So that's cool, but the Newton notation doesn't say anything about x, right? It doesn't specify the variable, but it is nice and elegant and simple, so we like to use it. All right, so there's your notations. One more thing. Sometimes instead of having a defined function or an output variable y, and sometimes you just want to say, do the derivative of this algebraic expression, and then like have some notation that says that. That's called a differential operator. So let's say you have an algebraic expression. I'm just going to represent an algebraic expression by this scribble, okay? You can take that, stick it in some brackets, and then put a prime on it, and that means do the derivative of this. Now, this represents the derivative of that algebraic expression. That's not a very common one. We don't use that very often because it's a little bit confusing, because it's like, okay, does that mean raised to the power 1? No, it's an apostrophe. It means prime. Okay, well, that's a bit, like, it's not clear, right? So the Leibniz notation is a little more useful for this. You can put the d over dx, and that means do the derivative of, with respect to x, of blank and then stick something in there. Or my personal preference is to just write dx, derivative with respect to x of whatever. So I'm going to be using this one a lot. We're going to be using dy over dx a lot, and we're going to be using f prime or y prime a lot. Those are probably the most common ones I will use, but I want you to know about them all so that when you encounter them, you know what they mean. So there we go.